Hello, my name is Jacob Magnon, and today I will be reviewing lab number 4 in Physics 2212, which deals with circuits. Let's get straight into it. The purpose of this lab is first to predict and analyze the behavior of different kinds of circuits, and then to measure the current and potential differences of these circuits using an online circuit simulator. We will examine the behavior of ohmic resistors and capacitors, then finally find the RC value of an RC circuit. Some of the main results of this lab are that our predictions are the same as the simulated results, and that a capacitor will take longer to charge when the resistor has a higher resistance. Also, we'll see how currents can depend on time, and this was my final RC value found at the end of the lab. The loop rule and the node rule are two important physics principles in this lab. The loop rule says that the round-trip potential of a circuit must be zero, and the node rule says that the current entering a node equals the current leaving it. Some other important equations are shown here, and then to find our RC value later on, we will use this equation, which is derived from this value of delta V. To predict the current of the circuit shown, we can use the node rule to confirm that I1 and I2 are equal. Then use the loop rule to create this equation. Solving for I, we get that the current is 0.02 amps. Looking at the simulated circuit, we are going to be using these written circuit components. After the circuit is set up, it confirms our prediction as the current is 0.02 amps. For the next part, we removed an ammeter and replaced it with a voltmeter. Since the circuit is now open, the current reading is 0. All the electrons are built up on one side of the wire, so the voltmeter reads a potential difference of 3 volts. At each point around the circuit, I measured the potential difference using the voltmeter, and the following values were obtained. These measurements support the loop rule since their sum is equal to 0. Also, in the bottom right is my graph of potential versus position around the circuit. As you can see, the final value is 0. Now, adding an ammeter parallel to a resistor as shown here in this picture, we notice that the current jumps up to 0.06, read by both ammeters. This is because the current chooses to take a path of least resistance, avoiding the second resistor in the path and continuing on. Less resistance will lead to a greater current. To find the value of resistance in each component of the circuit, we will use the delta V equation for resistors to get the resistance equals delta V over I. For each value, we will use the change in potential that was found over that component. For example, the 47 ohm resistor caused a 0.96 change in potential, so that is its value of delta V. Doing this for each component and using I is equal to 0.02 results in these following values. Now looking at an RC circuit, we are going to compare the charging and discharging times of a 0.2 farad capacitor connected to a 9-volt battery and either a 10 ohm or 20 ohm bulb. When charging and discharging, the current appeared to do the same thing, start off high and then approach 0 as time went on. These are my measured times of charging and discharging for the capacitor, first with a 10 ohm bulb and then a 20 ohm bulb. As you can see, the charging time was much greater when the resistance was increased. This is because when there is more resistance, the current gets smaller and the electrons move more slowly around the circuit. In the last part of this lab, we had to graph voltage versus time. This was done using a circuit of a 9-volt battery, a 0.2 farad capacitor, and a 30 ohm bulb. The capacitor was charged, then the battery was removed, and the capacitor was discharged. Over the next 20 seconds, the potential of the capacitor was tabulated. The initial value of V was equal to 9, which is the voltage of the battery. Using the equation natural log of V divided by V naught equals negative T divided by RC, I created the graph shown on the right. Using this equation, the slope is equal to negative 1 over RC, and as the line of best fit shows, that is equal to negative 0.1664. Now we can solve for RC to get the final value of 6.0096. For the discussion questions, if this experiment was done for real, the ammeter would have some sort of resistance that would cause the current to decrease. Next, if there was a real battery used to charge a real capacitor, this would not happen as instantaneously as the simulation predicts. It would happen fast, however the connecting wire would have some value of resistance slowing the process down. Some sources of error in this lab are rounding errors, negligence of resistance in the ammeters and wires, and some timing errors when recording the capacitor's voltage. To conclude, in this lab we were able to predict the current of a circuit. We demonstrated both the node and the loop rules, and also found the RC value in an RC circuit. We also observed how current is time dependent in an RC circuit. Thanks for watching.